Hi, my name is Han from Dr. Faye McNeil's group at Columbia University. Today I go over the work we did on the heterogeneous chemistry of calcite aerosols with HNO3 and HCl in the context of climate geoengineering. Here, climate geoengineering refers to a collection of proposed mitigation efforts to battle the rise in global temperature. This figure, taken from Lawrence et al. Recent paper, summarizes some of the currently studied areas, including carbon capture, utilization or storage, shown here in panel A, carbon dioxide removal from the atmosphere, shown here in panel B, and solar radiation management, shown here in panel C. For the purpose of today's presentation, I will focus on stratospheric aerosol injection, or SAI in short. SAI was inspired by studies on past major volcanic eruptions, such as that of Mount Pinatubo in 1991. Among the large quantity of material injected directly into the stratosphere, SO2 gas is especially notable, since it can quickly transform into sulfate particles. These particles can persist up to several years in the stratosphere, where they absorb upwelling infrared radiation, causing an initial stratospheric warming. By primarily scattering incoming solar radiation, they also lead to a surface cooling effect. Taking a deeper dive into the effects of sulfate particles on the atmosphere post-eruption, here on the left in red is the accumulated effects of greenhouse gases on increasing the Earth's surface temperature over the period of 1850 to 1991. In the 2 years after Mount Pinatubo eruption, there was a significant drop in the surface temperature that quickly surpassed the increase caused by greenhouse gases over the prior 140-year period. Despite the temporary surface cooling effect, 3 months after the eruption in June of 1991, there was a spike in the monthly average mean temperature in the stratosphere as much as 2.5 degrees C compared to the prior 26-year mean, depicted here by the horizontal bars. In addition, sulfate particles were also observed to negatively impact stratospheric ozone. The global mean ozone from the period of 1979 to 90, depicted here in the dark green line, dropped as much as 6% by 93, shown here in red. As a result, alternative particles have been proposed that could cool the Earth's surface temperature while minimizing the negative impacts in the stratosphere. Calcite aerosols, especially, often used as a proxy for mineral-rich dust in the lab, were recently suggested as one of the seeding options due to its lower risk of stratospheric warming and ozone depletion based on Dr. Keith's 2016 modeling study. In that study, the global ozone impact from a variety of aerosols was modeled, including calcite shown here in red and sulfate in yellow. The study modeled a range of gas uptake coefficients, or gamma, on calcite aerosols, since close to none is known about its heterogeneous chemistry in the stratosphere. Moreover, little is known about calcite reactions with stratospherically relevant gases, such as N2O5, HNO3, and HCl, even at room temperature. These gases are important in the stratosphere since they are reservoir species that directly affect ozone catalytic loss cycles. As a result, we've been studying experimentally the reactions between calcite aerosols and two trace gases, HNO3 and HCl. First, we conducted studies at room temperature where we investigated the reaction mechanism listed here with an FTIR. We also studied the reaction kinetics using both the FTIR and a custom-built quadruple CIMS. You can find the details in our recently published paper in JPCA. In the interest of time, today I'll focus on the kinetics results only, especially from the aerosol flow tube CIMS study. Here's a quick overview of the AFT CIMS experimental setup. On the top left, we have a dry calcite aerosol generation process where we remove larger size particles inertially. We monitored the relative humidity and temperature of the flow with a hygrometer. Calcite aerosols reacted with the gas phase species inside a flow tube reactor. The flow tube was coated with a thin layer of halocarbon wax to minimize wall loss. At the outlet of the reactor, the aerosols were continuously characterized with an SMPS. Since calcite aerosol surface area fluctuated over time due to the dry powder dispersion method, we designed the aerosol flow tube CIMS experiment such that HCl gas was delivered via the injector at a fixed position. We will go over more details in the next slide. To continuously monitor HCl gas depletion from reacting with calcite aerosol, we used the CIMS with SF6- as the reagent ion. We chose SF6- since it could react with both HNO3 and HCl. So SF5Cl- is the main ion to monitor for the reaction between calcite and HCl gas. Here we're showing a time series graph of SF5Cl- signal intensity for one experiment. The orange panel here represents the period when the aerosol flow was off, while the blue panel represents the aerosol on period. For each experiment, first we stabilize SF5Cl- signal intensity, as indicated by the red dots. We then introduce the aerosol into the flow tube, leading the signal to drop immediately. Once the signal stabilized as shown with the green dots, we turn off the aerosol flow while maintaining a constant total flow rate. We repeated that off-on process 3 to 5 times in each experiment. For all aerosol flow tube CIMS experiments, we kept a constant HCl concentration. Here we're showing a graph of SF5Cl- signal depletion from a representative experiment. On the y-axis, A and A0 represent the signal when aerosol flow was on and off, respectively. The linear negative correlation between the natural log of A over A0 and calcite surface area confirmed that calcite was depleted by HCl gas via pseudo first-order kinetics. The slope of the weighted least squares fit represents the observed first-order rate constant, Kops. After every aerosol experiment, we conducted a wall loss experiment. Keeping the total flow rate constant with the aerosol experiment, we introduced HCl into the flow reactor at different injector positions by moving the injector outwards periodically. By examining the change of SF5Cl- signal intensity in the absence of aerosols as shown here on the y-axis versus the injector position, we calculated the wall loss rate constant, Kwall, for each experiment. Knowing Kops and Kwall, we derived the true first-order rate constant, Ki, using the Brown iteration method. After we graphed Ki as a function of calcite aerosol surface area, we obtained the experimental uptake coefficient from the slope of the weighted linear fit. Using Fuchs and Sertigan formula to correct for non-continuum effect, we arrived at the true reactive uptake coefficient, or gamma. This correction was found to be negligible in our case at less than 5% for all experiment. Here we summarize the kinetic results from both the FTIR and CIMS studies. Since we didn't cover the FTIR studies in this presentation, the details of the FTIR experiments and their uncertainties can be found in our paper. In general, those warranted us to set the CIMS result as the upper bound of the FTIR kinetic results. Despite the uncertainty in the FTIR study, it was important for us to perform reactive uptake experiments using both the FTIR and the CIMS techniques on calcite particles generated from the same source in the same manner. These kinetic results also give us a benchmark for our low temperature flow tube studies. More importantly, we can narrow down the range of possible gas uptake coefficients on calcite experimentally and further confirm whether there really is a positive global ozone impact, as illustrated here from Dr. Kidd's modeling study in 2016. For HCl gas uptake on calcite aerosol, in the literature, there's only been one other study by Sanchi et al. Under similar conditions, shown here in the last row of this table. This study resulted in an uptake coefficient 1 order of magnitude higher than our result, 0.13 versus 0.013. This discrepancy could be due to several factors, including the differences in our techniques. They used the geometric surface area of the Knudsen cell as a particle surface area, whereas we used the SMPS measure and corrected aerosol surface area. Using the geometric SA of the Knudsen cell has been found to yield an upper limit of uptake coefficients values. In addition, Aerosol flow tube techniques minimize issues such as diffusion limitations and uncertainties in exposure surface area compared to using a nuts and cell reactor. There have been numerous studies on HNO3 gas uptake on calcite aerosol conducted at room temperature. However, the reported uptake coefficient vary over several orders of magnitude, as we can see in the third column of this table. The wide range of uptake values could be due to the differences in experimental technique and calcite particle type. Our HNO3 reactive uptake coefficient, shown here in the first row, is closer to those from the wet experiments, where either the relative humidity was high or the particle was generated from a solution. The wet experiments are included here at the top of the table. As a result, our HNO3 gamma is much higher than those from the dry experiments, shown here at the bottom 4 rows, with the exception of Sanchi et al. Study. The relative magnitude of HNO3 uptake coefficient versus HCl uptake coefficient in their study, 0.3 versus 0.13, which we mentioned in the previous slide, is similar to that of our own study. This photo confirms the observation we made with the FTIR study that calcite aerosols have a CaOH HCO3 termination layer due to a hydrated surface even under dry conditions. Specifically, calcite aerosols were observed to absorb atmospheric water vapor that persisted even when heated under a vacuum oven. Calcite heterogeneous chemistry with HNO3 therefore is dependent on the aerosol exposure to water vapor. And with that, I would like to conclude my presentation by thanking everyone in the McNeil group as well as the funding from Utopia Foundation. Thank you for your attention. If you have any questions, you can find more information in our paper, and you can also welcome to contact